Great to see you here. My name is Luc de Kuster, founder of the Kuster Academy, and welcome on our YouTube channel. If you're here for the first time or you didn't subscribe to our channel yet, this is the moment to click the subscribe button, click the bell button, and YouTube will inform you every time we have a new video. This video is about encryption. Encryption is very important. We're looking at all kinds of applications, and internet security is very important, but it's not something that we just need because we have internet. Encryption is something that is already existing for many years. When we look at encryption, what do we want to do? We want to keep the content of messages we exchange between trusted people, our friends, our colleagues, our company. We want to keep them safe from competitors, or when we talk about military applications, from our enemies. We don't want to share our information, and it's not about hiding things. It's about being sure that your trade secrets, your information is not shared outside of a group of people that should know about it. One of these things is, for example, the famous recipe of Coca-Cola. It's a trade secret, but there are other trade secrets that exist. Now, what we want to do, we want to send and receive messages between parties. We want to send something from a person A to a person B without other people being able to read what you do. Now, there are simple protocols. One of the very simple protocols that were used already 2000 years ago and before is what we call the Caesar cipher. Julius Caesar was using a very simple cipher method by changing the letters according to a specific pattern. But of course, there are all kinds of other elements that can be used. We can have a key that is involved to translate, to encrypt and to decrypt messages. We also heard stories about sending messages with invisible ink, so people cannot see it. They have to follow a specific procedure, so these are things that can be done. We also look at passwords that give us access to certain applications, to our internet, to our banking. When we look at the banking, we also use some variable keys. Remember or think about an RSA key when you have something like OT or some other app on your mobile. Those are apps that generate a key, and that key gives you access to specific applications. It's an extra layer of security. Think about the Enigma machine, the famous machine that was invented by the Germans during the Second World War. It was infamous. People couldn't decipher it, although they already found the basics of the Enigma machine in Poland, and the Germans knew about it, so they increased security, and basically the coding with the Enigma machine was basically unbreakable. Of course, we have the people like Alan Turing with his team. They were working on breaking the code. They realized it. They created the first computer to do this. Basically, when they found the code, and when you watch the movie, The Imitation Game, I don't know if everything is true historically, but for example, there is one moment where they crack the code and they find out that the Germans are going to attack a specific convoy, and one of the people of the team, his brother, is on one of those ships. It's impossible to warn them, because if the Germans at that time would understand that the code was broken, they would have the time to improve their code, and all the efforts were done or were lost. So basically, when you crack a code, you have to be sure that you use it in a good way, that you keep the secret, that you only use it in sporadic, intelligent ways. Otherwise, the other party will understand and they will change the system. We also had the code talkers. You may have heard about them. It was used by the US Army, but other armies also used it. They started doing it in the First World War. Instead of coding messages, what they did, they used Native Americans, Indians, speaking their native language, Comanche and other languages, to send messages in the clear, because almost nobody was speaking those languages, certainly not in Europe at that time. It was a quite interesting way of sharing secrets quite fast. You had to have the people on both sides, they could understand, and they also added some additional encryption to that. When I was in the military, we had a kind of coding system. It was a kind of chart with keys that had to be used, and we got those keys on our meetings. We received the codes that we had to use on the sliders, and we could cipher and decipher messages. Of course, you have to have the key, and that's one of the big problems when you're working with encryption and decryption, is that both parties have to have the keys. So basically, when somebody lost the coding system, or it was stolen, or it was taken away when you were a prisoner, well, the codes were known and all the codes had to be changed immediately. It's not very practical. Today we have other ways of doing it. We can use computers. We have all kinds of encryption protocols that exist, key exchange protocols, and we'll learn more about these things in the following videos about encryption. But in this first video, we're just looking into a simple encryption protocol based on modular arithmetic. All of them basically use modular arithmetic, but we're going to see how the Caesar cipher works and how we can improve the cipher to add more security. Let's have a look at this in a few seconds. The Caesar cipher was one of the oldest ciphers known, and what it does, it adds 3 numbers to the letters. So we move 3 steps in the alphabet. Now, the alphabet, we give the letter A 00 and Z is 25. So basically what we do, we add 3 to the letter. So when we look at C, it's number 2 in the alphabet. So 2 plus 3 is 5, or 05, and the 5th letter of the alphabet is the F. Now we do the same with the 25. We do plus 3, which is 28, but we don't have number 28. So basically we go back to 0 when we arrive at 25. The next letter is 0, 1, 2. And we have 28 modulus 26 is equal to 2, which is in that case equal, or 02 is C. For 04 plus 3 is 7, and the 7th letter in the alphabet is the H. Then we have 2, it's the same like this one, so we can immediately say that it's an F. And the last letter here, 07 plus 3 is 10, and 10 gives us the letter K. So basically, when we look at check and we encrypt it, we find FCH FK, and that's the message we send. When we know the cipher, we know we can go back in the other direction, and we use a similar protocol. Now, when we look at this, we can write this protocol in the form of a formula dealing with numbers between 0 and 25, the numbers of the alphabet, which give us the following relationship, that f of p, which is the transformation formula, is p plus 3 modulus 26, and p is between 0 and 26 not included. So if we put it in here, we look at f of 2, or let's say this one here, f of 25 is 25 plus 3 modulus 26 is in fact 2, hence the letter C. So basically that's what we're going to do. Now we have to be careful when we look at the letters. We may have other symbols. We may have other elements that we want to include in our message. So when we just have letters, we can use this cipher without a problem. But when we have other characters, like the ASCII characters, we have to look at different characters. Every letter, capital letter, small letter, every symbol has an ASCII symbol or ASCII number, and we of course have to adjust the modulus here. But that's basically the Cipher cipher to encrypt. Let's now have a look how we can use the same thing to decrypt the message. And we start from our message that we encrypted, and we should find check again. We encrypted the message, but now we have to do it in the other side. We have to decrypt the message. So basically we have to go back 3 spaces. So when we look at the original encryption formula, is p plus 3 modulus 26. We can say that k, the factor that we add or that we move the numbers, is in this case 3. And when we go back, when we decrypt, we have to go 3 places back. So we have p minus 3, p being the encrypted letter or the encrypted data. So when we say f is 0,5, so we know that f minus 1 of 5 is 5 minus 3 modulus 26 is basically equal to 2, which corresponds with the letter C. C is 0,2. Oh, this is interesting because f minus 1 of 2 is equal to 2 minus 3 modulus 26, which is minus 1. But when we add 26, because we work with modular arithmetic, we find that this is also 25 modulus 26, and we find the letter Z. H07, we have n minus 1 of 7 is 7 minus 3 modulus 26, which automatically gives us 4, which is the letter E. Then we have F05, so we automatically know that this will be a C. We did the calculation before. And here we have F minus 1 of 10, which is 10 minus 3 modulus 26 is in fact 7, and we have here the letter H. Now when we look at this, we can rewrite this in a more general form, and we call this basically a shift cipher. A shift cipher, why we move? Because we move with a number of places. And we can make a general shift cipher, which is P plus K modulus 26. And in this case, we have the K with the Cipher cipher. This is 3, but we can take any value that we want. And of course, when we have this, the decryption formula F minus 1 of P is P minus K modulus 26. So we can select different values of K to make it a little bit more complex, but we have some other improvements that we can do. We can create a better cipher formula, but it's still a weak formula when you look at all the means that we have today. How would you decipher a message? Well, we know in which language the letter or the message has been written. A typical way to find a relationship would be to find the letters which are the most used. For example, we know for every language what's the frequency of usage of specific letters, and we can start by replacing the message like that. It's a brute force approach, but it's something that could work. Of course, today we have better means to encrypt, and we are finding better ways to decrypt. But it's a game of cat and mouse. we find better encryption, we find better decryption, we have better computers, we have better procedures, and so on. So basically we're going to use that, we're going to improve the different ciphers. Let's have a look at a first improvement that we can introduce based on the shift cipher. Now we have an improved cipher, and that improved cipher is not only adding a number but is also multiplying. So we multiply the value, the initial value, with the coefficient a, we add b and then calculate modulus 26, and the GCD of a and 26 is equal to 1. So a and 26 are relatively prime, and we're going to use this in the following approach. Now, when we start here, we can say we have minus b from both sides, so we adjust the formula. C minus b is congruent with AP modulus 26. Now we know that A modulus 26 has an inverse A, for which A times A inverse modulus 26 is 1. So what we're going to do now is to multiply both sides with the inverse of A modulus 26. So we find C minus B times A inverse is congruent A inverse times A times P modulus 26. And we can rewrite this as C minus B times A inverse is congruent with P modulus 26. Since C minus B times A inverse and P have the same remainder when divided by 26, I can say the final expression is that P is congruent with C minus B times A inverse modulus 26. And this is basically f minus 1 of P in this case. So we have the encryption cipher and we have the decryption cipher. And let's do a simple exercise to show how we use this formula to encrypt one letter and then to decrypt it again, and we should have the same result. Let's apply the formulas to encrypt and decrypt the letter L, which is characterized by the number 11. So we can basically say that C, the encrypted value, is f of 11, is 3 times 11 plus 7 modulus 26, which is equal to 33 plus 7 modulus 26. 26 is basically 14, because this is 40 minus 26 is 14. So we find the letter O, which corresponds with the value of 14. Now we go to decrypt. We find P is f minus 1 of 14, the value of O, and that is equal to the C, which we have is 11, minus 7 times 3, let's say times 9. So we have 9 here, modulus 26. So we find here, oh sorry, it's 14, it's not 11, it's 14. And we find here 7 times 9 modulus 26. And we can say that this is 63 modulus 26. And we can say that 63 is 2 times 26 plus 11, we have 52, plus 11 is 63. So we find here 11, and we find the original letter again. So basically with this cipher, this more complex cipher, we can find, using the properties of the congruences, basically we can say that P is congruent with C minus B multiplied with the modular inverse of A modulus 26 is modulus 26. And when we put the values in here, we also find here 7 times 9. Basically we have the same thing like we have here, so we find the same value. So we have an encryption formula and a decryption formula, which is a little bit more complex than the original one. Anyway, this is the end of this video. Do not forget to have a quick look at the text below the video. Below the description you find all the links to our courses. You can find more courses on our website, thecusteracademy.com. But it's very important, when you look at the links to the courses, there is each time a voucher, a coupon that you can get, that you can use when you buy the course to get a great discount. Anyway, if you didn't do it yet, it's the moment to click the subscribe button and click on the bell button so YouTube will inform you every time when we have a new video. Thank you very much, and bye bye.